Is it live? Hello, hello. I have it open on my phone. And actually I wanted to use my laptop before the plastic will be completely dissolved. Yeah, so it's time to change the laptop. And what's there? Okay. Oh, I haven't prepared myself. And actually, I prepared the fishes to have just air, so I switch off the pump. But I will use the proper microphone. Okay. So I will be more audible. And that might be interesting for some of you ladies and gentlemen. All the best for the ladies, as it's International Ladies Day. So I have this bonus for all of you. You can collaborate well. I wanted to show what I'm doing for my hobby from time to time, because well, I don't have the one main hobby, but rather I'm switching between couples. So bees, as it's almost spring, bees is my another hobby. So I was with my bees today as well. It's a very nice day, and yeah, to not talking too much of what was important, but you see here what is important. To work on this hobby means working with drones, trying to figure out how they work, and use some math as well, to get to know some physics, some electronics, programming, general thinking, critical thinking, having critical times. That's why it's good to have some other things to do, if you know that you can have something from it. I believe it's actually, this is my approach, and I think this is a good approach. So what board I have? This is the basic one. So this is STM32 Nucleo G. Let me check. G431 KB. 431. Very small, very compact, and I've checked that for regular quadcopter with 2 inertial measurement units and 1 magnetometer. In that way, that this is the slave electronic that is connected to this master inertial measurement unit. So I can use just 2 pair of I2C wires, and of course the plus and ground. And all 3 sensors are connected, so where ground is needed, you see on that way there are some additional cables that are used to bring the signal to the sensor. So there is more than one ground, and sometimes more than one power cable connected to the pins there. It is glued, but you can check that with documentation, and also how to use the slave connection, to use just one I2C. There is second I2C, and actually I did that because for filtering the data and the noise, that one which is without the magnetometer is much faster, and the one that is getting the data from IMU, so linear acceleration and angular velocity from gyroscope, and that one have same, but that one in addition have the same, so all have XYZ, so acceleration and gyroscope, and magnetometer also have in 3 axis the informations, and that gives longer delay to get data. That's why I'm more often in this loop that the quadcopter is working. More often I'm taking acceleration and angular velocity from that one, and there is more information, but is the time domain and the period is longer in that case. I will show maybe another one. I was starting for bigger drone, and it allowed to connect much more equipment. This is similar, and this is also Nucleo G, but this time G47RE. It is also one user button, and was using for calibration, switching on calibration and off with IRQ. So the interrupt procedure on the MCU, and this is much larger, so that is very small. It allowed to connect 4 motors as well, having those pins, 4 motors and 4 radio channels, and mainly in addition, as I mentioned, 2 I2C or I2C communication, so 2 wires means 4 wires for 2 connections. Okay, and actually that one there is also the pressure sensor, or is Bosch sensor tech. It's working very well. I would say it's not expensive. It's widely available. This is not designed for drones, but for tests, for cheap tests actually, and some POC, this minimum viable product. So something that you can learn. Actually, it is very good. So that's for later. But I was starting with F401, and I can mention maybe okay, that's on my GitHub. You can find some sources if you are interested in this stuff. So in the projects you can check. Welcome to repository. Yeah, there is a drone F411. It has about 1 year. I stopped because, well, there are it's stopped to I needed time actually to sort out stuff, and I think I will be using some time currently to work again. In the meantime, actually, I was preparing also the different boards. It was the time is always busy, so it is how it works. Okay, so we have that one. I have prepared also the frame with the motors and other stuff in different room, but it's not important. This is just quadcopter, and the motors with electronic speed controllers and beds for MCU. There is another bed, so I will try to make it noiseless as much as I can. So this is the current work. You can check that stuff if you are interested in and actually it was using 2411 because I was trying to use GPS, some servos. Actually, I was learning in that time, but currently I was thinking it's much better. It's much better actually to start from the beginning. So yeah, this is actually the version of the Cube ID is 1.17, so I was upgrading a couple times, but I show still there are some issues, at least with G431, or I was not reading documentation properly. Okay, so actually if you can start a new project. Let me just, if we'll ask, okay, that will, I will show maybe, you know, how to set up the project and what setup I did for this drone. So actually there is, as I mentioned, I2C protocols that communicate with MEMS, which are microelectronics modules, or yeah, something like that. MEMS, yeah, microelectronics sensors maybe. So there are some mechanical parts as well that allow to measure. In that case there is linear acceleration and angular velocity, and then there is strength of magnetic field in 3 axis. That's why it's MEMS. And this is very, very micro, because if you can see, that part is responsible. There are some resistors to pull up the path, and there are same also like resistor, and the middle one, that one in the middle, I'm not sure if you see that. That box is the real sensor. Rest is the board and the pins. Okay, that's taking. Okay, it's ending. Maybe it's ending. So what the configuration there is? The yaw is it's yaw from the radio. So from the transmitter receiver pair, there is roll, throttle and pitch, so 4 radios used. The timers are used, I think one sensor is using, let's see, if I click there, can I click there? No, because that is, now can I click? Okay, let's wait. Okay, we are creating a new project, so that's different context. It's a bit slow. Why so slow? Oh, this is the new. Selection is required. Okay, so what we can select. So you can filter based on what you need actually. Product info, segment, series. So G4. Is there any G4? There is a lot of G4. Package line. Mainstream MCU. That changed a lot, and actually I haven't had it open for some time, doing different things. So okay, STM32 G431 G4. come on, I will close it for a moment. It also doesn't want to be closed, and that's bad. Okay. But in the meantime we have opened the timer, so we need to pick up from there. Timer 1, what it has. So this is just the timer with 1 megahertz, so it is 1 microsecond. Microsecond, so not millisecond but microsecond, yeah. Not nanosecond but microsecond. And this is from this configuration. So I set up the clocks for peripherals to 150, as this board have maximum of 170, 170, and the other one, the bigger one, probably same. So this is the setup for the peripheral. So 150 for I2C, and mainly it is not very complex board. It doesn't have many legs there. So, and actually yeah, ladies, that's yours day. So if you are there, I hope you will take something for yourself. Going back to the configuration, so this is the timer. I have one timer used for what? Okay, I have R2C. One timer used to measure the speed of the operations. The other timer is used for motors, so I'm using this counter period is most important. Rest is as it is. PWM mode 1 for those channels, and that is one shot 42, so 42 to 84. So with that clock and that counter period, you can take good results. So it doesn't have electric ducted fan. There are just brushless electric motors, the standard ones. There is input capture, so timer number 3. Where is, so we have four channels, as you see. The timer number 2 have 2 channels for motors, and from documentation you need to figure out what connection, what leg you need to use to connect to the speed controllers, what legs you need to use for IMU, one IMU and second IMU. There is LED also, one LED that is there, and I think I'm using that also for arming. So it gives green light when the arming is done. So I'm using the startup procedure with transmitter to be down to the center. Such procedure, and the other timer is also for 2 other motors, and one more timer is used for the delay that is used by AMUs. Okay, let's just quickly connect that. Let's just connect. So this is just a short introduction. Okay, so I won't be using radio and motors. That part mainly was done. We have main there. Oh, one more thing. So there is also connectivity. There are I2C, and mainly that's it. I'm not using any other fancy stuff that is provided with this board, with this microcontroller. So no middleware, no BSP. Okay, and in the project manager, so what I selected there, so generate graphic. Okay, so the separate files, pair of C and H per peripheral, so it's easier to manage. As you see, there is I2C in the separate file, have RTC, have timer, and there is catalog with my stuff actually. And it's very similar to what you will find on the GitHub. There are just small improvements and changes. Also, I'm not sure, but yeah, the IMU, what okay, this is, so I'm using also the internal interrupt controller that IMU has. So there is interrupt configuration also, and you can easily set up that. Okay, where is that used? Because I don't remember. Maybe even not there. Oops. Okay. This is for I2C gyro data, internal interrupt. Couple good informations, because you have information when the data is ready mainly. Okay, so that loop that it's working. I'm not using the RTOS. Maybe in some future, but not yet. So the bridge is it's similar in the GitHub, but their bridge was connecting one F411 that was having information like from the operator, and the radio signal was sent to through UART to second controller. That was because of lack of the legs there, because I was using like GPS, some more motors, some servos, too much stuff actually. So that's why I stopped working on the previous project. I started to check different options, and it happened that the simplest one, and like preparing the engine, let's say, so also the math, the physics, I'm checking rotation metrics and Euler angles and quaternions, and well, there what I can say, so the most proper for orientation and rotation representation are quaternions, because they use 4 numbers. Euler angles have 3 numbers, like 3 angles per each axis, but there is division by 0 and some singularities, let's say. This is there are some issues with that, so you can't use 90 degrees, for example. You need to not allow some angles. Rotation matrix use 9 numbers, and there are some zeros, but okay, you can remove zeros. Okay, starting from rotation matrix again. So you see there are a lot of zeros, so it's not required actually to have that time for the MCU to multiply something by 0 like it is for let's say step-by-step operation. You can use the shorthand, so you can calculate it and you will get some shorter equations, but it's still there is 9 numbers, and I'm not trying that with the MCU. I'm simulating that on the Visual Studio Code, checking if the matrix Euler angle and quaternion gives proper results, having some help from internet online website with the tools like to check that stuff about the orientation. So this is the current state of the works. So mainly the board is prepared, the drone is also prepared, just the heart and the mind, the brain, better saying, for the drone is not programmed properly yet, but let's simulate maybe. Okay, and bridge calibration, this is off because to go to the other process, like to have the HRS, so amplitude heading reference systems. It's this is the abbreviation HRS. That's complicated. Okay, and that is also commented, and flight motors, that actually there are the comments, so I'm not using that. This is prepare, and also in the GitHub this is prepare as well. You need just to do the math, physics, and you can work on it as well. Let's run it. Stop bullshit, yeah? Let's run it. So we have the setups. There is and what is important, the debugger is there, so you don't need to have additional stuff to connect. You're just using USB and is there. Okay, so I will run it just. Okay, this is how it's starting. Okay, and then with what is there, F6, you can go through the steps. Okay, so there is initialization for GPIO, the timers, the peripherals, so I2C, real-time clock, I2C, and other timers for internal input capture, and for PWM generation for motors. Input capture is for radio. Okay, so we are going there. Okay, it's working fine. Pre-init, you can find that also in the GitHub. Bridge init, RC init, we don't have it. The timer init. Then we initialize the IMU, and we are starting with collecting data, and we have this data ready interrupt actually. So maybe if I will go there, so I'm checking the data ready interrupt, and when the data is read, that flag is released, so it works in the loop. So I'm just collecting data, okay, currently in that case, and we can see that the other accelerometer is also providing the data. That is the faster one, and a gyroscope for angular velocity with 3 axes is also giving the information. So this is what we will be filtering, and the first one also have the magnetometer. And if we run it, so we'll see this is changing very fast, and I'm collecting 10 informations to have historical data for to see how it progress, let's say. So what is the rate of change for the values? That is my idea actually to check. And the IMU without magnetometer is you can see that, but it's very fast. How we can I don't remember the code exactly. The result, what is the result? We have timer. Okay, I'm not getting that data. I need to check. I was not working with this code for a couple months actually. Okay, we have data ready. Okay, so if I'm changing the orientation, so magnetometer currently this is to the north somewhere. Yeah, so that needs to be filtered out, the noise, so the statistic needs to be done for the components to see what is the accuracy and actually the precision. So how often it gives same data for same conditions, and accuracy is how close is to proper conditions actually. Oh, so I've disconnected that. Oh, that's bad. Why? Okay, let me run again. Oh, what's happened? Let me run again. Okay, let's go with it. So where we are. Okay, it's working. I'm not sure what's happened. It was disconnected. Okay. Okay, I'm not sure how long it takes, but that was actually a brief introduction, and oh, that's crazy. That's crazy. So let's see the gyroscope angular velocity. That gives some information, and that's the topic. Mainly to filter the data, to take data, to put to the algorithm and stabilize the flight. Actually currently to have just a hover and landing, and then we see what next. Okay. I hope you enjoy, and I